Hello. The purpose of this video is to help describe not only what does the central limit theorem say, but also how to use the central limit theorem to calculate probabilities, such as the probabilities in this question. What is the probability of seeing not just a certain baby, but also what is the probability of seeing an average from a sample? So I will start by reading the question and then answering these questions. So, according to the article, Are Babies Normal? By Tracy Clemens and Marcella Pagano, it was published in the American Statistician. The birth weights of babies are normally distributed with a mean of 3,358 grams and a standard deviation of 588 grams. What is the probability that a randomly selected baby will weigh between 3,100 grams and 3,600 grams? Now, first, I noticed that this question is describing baby weights, describing data that is normally distributed. And that means that to calculate any probability related to seeing that data that is normally distributed, is something that I can do using a normal distribution probability calculator. To do it by hand, you would need calculus, but to do it using probability calculators, we can even search on the internet a normal distribution probability calculator, and of any of the options that appear. For example, the first option that appears when I search in Google will bring me to a calculator that looks like this, a normal distribution probability calculator, which gives you space to enter a mean and a standard deviation, and selecting certain options will calculate a probability. So I'm going to use this calculator to answer the question that is posed in this homework assignment. Returning to the question, what is the probability that a randomly selected baby weighs between 3,100 and 3,600? So if the mean of the baby's average weight is 3,358, then I can describe that distribution over here with a mean 3,358 grams. Notice the calculator changes. And so then using the standard deviation of 588 grams, entering a standard deviation of 588 grams, now I have a sketch that describes the distribution of all of the baby weights, the grams possible for the baby weights. The question also asks, what is the probability that the babies that you pick weighs between this and this? In other words, I am going to go in the calculator to calculate this probability. I'm going to select the option between, and here I will type in the grams that were given. So this calculator will calculate for me what is the probability for data of this distribution, the probability of seeing a baby that weighs between 3,100 and 3,600 grams. When I click recalculate, I see that the probability of a randomly picked baby will be 0.3293. That is probably 0.03293, and rounded to 3 decimal places, that is 0.329. So you've now used a normal probability calculator to answer the question of what is the probability that a randomly selected baby weighs between this and this. Now notice, and I'm going to move on to part B, and notice that the question is a little different. What is the probability that the average weight of 30 randomly selected babies? So 30 randomly selected babies, that is going to be a sample taken from a population. So for example, we are no longer looking at a population. For example, this is a population with some mean and standard deviation, like our 3,358 grams mean. But instead, I'm interested in examining the way that the means are distributed when I have samples of 30. Now this says 25. I do not have an option of 30. But my question asks me, oh, if I were to be taking samples of 30 babies, from a population like this, how will, for the sample of 30 babies, how will the mean, and if I did this again and again, how will all of the sample means behave? If I repeat this not just one time, 2 times, 5, 10, if I repeated thousands and thousands of times, I will see how the sample means behave. Apparently, they are, we can see, normally distributed. And this mean and this standard deviation are related to the mean and the standard deviation of my population. By the central limit theorem, we know that the mean of the possible sample means this mean is going to be the same as the population mean. And the standard deviation of these means, standard deviation equals to the square root of sigma, if you will, the square root of the standard deviation. It will equal to the standard deviation divided by the square root of the size of the samples you're taking. In other words, the central limit theorem tells us that, and we'll try and find a picture. The central limit theorem tells us that, here we go, that if see this picture, if you have a population mean, no, there we go. If you have a population of data, normally distributed or not, if you take samples of certain size, then the sample means, notice it's not the data, but the sample means, the blue histograms, will look normally distributed, and the standard deviation can be calculated as sigma divided by the square root of n. In other words, to answer this question here, I need, what is the probability for an average weight of 30 babies? I need to calculate the mean and the standard deviation for the sample averages of the samples of 30 possible selected random babies. So I will again be using a normal distribution calculator. However, the mean and the standard deviation need to be the mean and the standard deviation for the sampling distribution, not the population. So by the central limit theorem, the mean of this distribution is the same as the population mean, and therefore this mean will still stay the same. This mean will be the same. The mean of the blue histogram will be the same as the mean of the population. The mean of my sample averages of samples of size 30 will still be equal to the population, the average of the baby weights, 3,358. What will be different is the standard deviation. And we can use the formula from the central limit theorem to calculate the new standard deviation. The number that needs to be put in this formula, the number to calculate to put in this box we can calculate with this formula. So the standard deviation, as we are given it, is 588. 588. But we are going to enter into the calculator the standard deviation. We will enter using the formula and calculate the number 588 divided by the square root of n, the square root of the size samples we are taking, the square root of samples that are size 30. So again, we are going to now calculate the standard deviation that I need to then put here for my normal probability calculator. And I'm going to calculate it using this formula over here. So I will take the sigma, the given to me sigma of 588, and I am going to divide that by 588, and it will be divided by the square root of 30. 30 square root. Notice I use these parenthesis symbols to do the order of operations. In other words, 588 divided by the square root of 30 will equal to 107.3536322. And so this is the number that I will use for the standard deviation in my normal probability calculator. This is the number, this number that I will use in the space for the standard deviation. Now, I recommend you keep as many decimal places as possible. I'm going to copy this number, but you may not, the calculator may only allow you some of the decimals. I'm going to click and copy this number and paste the number as many as I can here. Right click paste. It only allows 4 decimals, but I have now pasted my calculated standard deviation into this calculator. And now I am able to use the calculator, the new mean and the new standard deviation. In other words, I have changed my calculator to be calculating probabilities about sample averages, about probabilities involving this distribution. Not the parent population, not the baby weights, but if you will, the distribution of the possible sample averages for babies of samples of size 30, not size 25. Babies of samples of size 30. The last step that I do is I return for this question asking me, what's the probability that the average weight of 30 babies is between 3100 grams, 3600 grams? I will again use my normal probability calculator because I know that my average weights, my averages are normally distributed and normally distributed with this mean and this standard deviation by the central limit theorem. So what is the probability that the mean will be between 3100 and 3600? When I click recalculate, there is my probability, my answer. What is the probability of seeing a baby's average for 30 babies? What's the probability of seeing a 30 baby average weight between 3100 and 3600? The answer is about 97.98, about 98%. I can copy this number and then paste it into my homework question. This is the answer to this part of the question. If I round to 3 decimal places, and this I will need to raise this number up, 3980. Again, if I have 4 decimal places, I round this number up. I have to round up the number 9, but I have to, in order to round this number up, 79 becomes 80.